Good. So Kelvin's foam problem. So Kelvin wants to know how to partition space into bubbles. So he calls it foam. Basically, you want to partition space into cells, tiles. Choose the name of say volume 1, and want to minimize the surface area. So how to partition Rn into say, call it bubbles, call it whatever you want, tiles of volume 1 with minimal surface area. So how would you do this in, say, 2 dimensions? I just want to motivate the problem. So dimension 2. Okay. So one easy way to do it is just partition plane into squares, right? Using square lattice like this, right? But then if you look at and each one is a volume 1, but then the surface area, in this case, perimeter is 4. This gives me perimeter of 4 of the square, right? It's a 1 by 1 square. Can we do better? Try a beehive. Yes, thank you. And let me take that from here. I have it ready. I don't have to draw the beehive. It never comes out, right? Here we go. Okay, that's the beehive. So what's the history of the beehive? Well, actually, it was conjectured to be optimal already by the Greek. Actually, Pappus of Alexandria. It's a bit later. It's actually 330 AD. To show this is really the optimal partition, like the least surface area, the least perimeter, actually took a while. It was eventually proven by Hales, the same Thomas Hales from the Kepler conjecture, if you know, but packing spheres in 3 dimensions. Apparently, it was a piece of cake for him. Compared to only 20 pages, it was. After he was finished with the Kepler conjecture, I thought let's spend the weekend and do that. So he basically showed this is the optimal thing you can do. If you calculate, this is a good exercise, if you calculate the perimeter of a hexagon of volume of area 1, it's 3.72. So notice this, this for any shape, or they have to be anything. So I believe they don't have to be the same shape, any partition. So there's some variants of this question, which you soon won't have to worry about, because we will work with very nice repetitive shape, but I think it proved it for any partition. Yeah. Okay, so this actually forms a lattice. We'll get back to lattice later, but this is, of course, the hexagon is very nice. This also shows up in nature, like that's why it's called the beehive, of course, that was discovered by Apis mellifera. I checked this 100 million years ago. So, okay. Well, I'm serious. Somehow they realized that this is the best way to create like chambers for their whatever it's called, using the minimal beeswax, right? That you have to build the walls, cell walls from. Okay, so this is dimension 2. Everything is nice and understood. Things get already messier in dimension 3. More interesting, I would say. So if you just take a cube, there are 6 faces, so the surface area is 6. But already Kelvin realized that you can do better than that, 1887. And that, again, connects to well-known lattice packing, lattice structure. And the way you do that looks something like that. So the 4 cells shown here, it's a truncated octahedron, whatever that is. The details don't really matter. You get surface area of, the number somewhere here, 5.306. 5.306. Now, one thing that kept that Kelvin already knew is that if you look very carefully, if I can zoom in, this is not a bug. You see there's some curvature there. It's not really flat. It's not really truncated octahedron. It's not a polytope. It turns out this was known to Belgian mathematician in the 19th century, that whenever you have this optimal form structure, the angles at which faces join must form 120 degrees. So some local optimality conditions. So what you're seeing here is basically Kelvin took the truncated octahedron, this polytope that ties space, and slightly push the faces to make it in the right angles joining. That decreases tiny bit the surface area. For a century, this was believed to be the best way to partition space, the best form, but this was disproved by physicists in the 1990s. So this is Weir and Phelan in 1994. And they actually took their inspiration from some from chemistry, from physics. There is a crystal that is formed. It's called the Klarreich, and it actually forms a more efficient structure. And you can see it here. It's not the same translation of the same shape over and over again. Okay, so it's more involved in that sense, and it gives slightly better surface area of 5.288. So what you want is basically partition space into those bubbles. Each bubble must have volume 1, so they're all of volume 1. But you want to minimize the average surface area. Yeah, because they're different, they're not all the same. So in this case, it would be the average surface area. The amount of material you have to use to build those. Kind of per cell, how much surface area you use. Yeah. So the situation in dimension 3 is still unknown. The optimal solution is unknown. Luckily, this is not the topic of today's talk. So I just kind of background will very soon go to high dimensions. So I don't know anything really in 3 dimensions. Everything is easier in n dimensions. Okay. So Kelvin actually built this. So he took metal sticks and then tried to build. It's called Kelvin's box spring. Dipped it into soap, took it out, and kind of tried to see the thing before and the same thing. No, so you could get those things, but nature is not always cooperative. So what I tried to do next is take like a syringe and try to actually generate. This was done later, like with a syringe, try to generate those bubbles and hope that you actually get those shapes. And I think what happened by the time that they finished, like I think like 2,000 of those bubbles, the first one already dried out. So, but actually this is something that Weir and Phelan said, that there was too much theory, not enough experimentation. And they actually were able to generate this using straws. They blew into that air, and they managed to create such a structure physically. So it can happen sometimes. Nature also optimizes that structure, but they needed some help from the bubble blower. Okay. So again, the exact number is not known, but we have some ballpark of what it should be. The question we look at here is what happens asymptotically. N goes to infinity. What are the high dimensions? What are the best ways to partition space? So there's a lower bound. There's an easy lower bound that follows from the isoperimetric inequality. Isoperimetric. Which basically tells you that if you have volume 1, then the best surface area you can get is just a sphere. Right, so that gives the following. Any volume 1 set has surface area at least square root 2 pi en. So in dimension n is always a dimension. The surface area scales like square root n. The numbers, the fact that square root 2 pi e doesn't matter. It just happens to be the surface area of a ball of radius 1. And I'm ignoring some low order terms here and everywhere. So the exact expression is slightly different, but asymptotically that's it. So, you know, how do you actually get there? How can you prove an upper bound? Can you find a way to partition space? The easiest is to just take a cube. So you can take a cube, of course, 0, 1 to the n, like we did before. And that gives 2n, right? Because we have 2n faces, each of area 1. Okay. Can we do better? And yes, so we can do better. And this will allow me to introduce a simple claim that allows us to bound the surface area. I'm sure it has a name. I'm sure it is, if you look at textbooks, probably it's well known. I'm sure it's well known. But let me show you nevertheless. I don't have a good reference, but I'm sure it's well known. So basically the claim is this: how do you show that the body has small surface area? How do you even measure surface area conveniently? So there's a trick. There's a nice convenient thing you can do. So you take a convex body. So I will assume the body is convex. That makes it much easier to argue about, as you'll see in a minute. Assume a convex body K contains a big Euclidean ball. So basically what we care about is in radius. We want the body to contain a big ball inside it. So contains a Euclidean ball of radius r. Euclidean ball of radius r. Then you have a bound on the surface area. Then the volume of the surface area of K, that's how we denote it. So the surface area of K is at most n over r times the volume of K. Okay, so if the volume of K is 1, we have a bound of n over r on the surface area. Let me just write this equivalently, because this will be useful later. So I will just divide by the volume on both sides and write it in this way. The quantity on the left will show up again later. So let me just say a few words about this. This ratio of the surface area to the volume, it's something that will be very natural in this proof. Let me just warn you that this is contrary to other quantities. This is not scale invariant. If I actually scale up the body like by a factor of 10, so the volume grows up by 10 to the n, but the surface area only grows up by 10 to the n minus 1. So this actually is like, because minus 1 homogeneous in scale. So if I scale up the body by 10, this quantity shrinks by a factor of 10. So this quantity will show up later. That's why I already want to prime you to think in this way of this ratio. But if the volume is 1, this gives us a bound of n over r on the radius. So how do you prove this? Actually, the proof is surprisingly simple. So without loss of generality, assume that the ball is centered at the origin. So I just center everything at the origin. It doesn't really affect anything. Okay, so B2 is just my notation for volume ball of radius 1 around the origin. This is radius 1 Euclidean ball around the origin, around 0. So then what do we get? So the volume of the surface area, I should say, of K. So what is surface area basically? Surface area is that you can add a little bit to the surface, check what the volume is, and then let that delta, that thickness that you added go to 0. That's the definition that I'm using here for surface. Okay. So is the limit as delta goes to 0 of the volume of K plus delta B2. So a little bit, I'm adding some Minkowski sum, so I'm adding a little L2 distance of delta around the ball, around the body. and I'm subtracting K. I'm showing a picture of what this means, and I'm dividing by delta. That's basically the definition of surface area. So just to show in a picture, right? If I have, say, a square, what I'm doing here is kind of adding a little bit delta around the square, and I'm getting some round corners like this. Okay, so this is supposed to be here delta thickness. And what I want to measure the volume here in this little region of thickness delta around my body, and then let delta go to 0 and look at this limit as, you know, as the delta goes to 0. That's just a surface area. Okay? So if you believe me, the surface area, I think we can now complete the proof, because instead of adding delta B2, I'm going to add a scaling of K itself, because K contains a ball. So K is only, only bigger than the ball. So I can upper bound or bound this from above by, I have 1 plus delta over R K minus K. So I'm replacing a ball of radius delta with my actual body K scaled by delta over R, right? Because K contains a ball of radius R, so delta over R K contains a ball of radius delta. So I'm just replacing in this case, that would be here a ball contained inside my body, and I'm replacing the thing I'm adding. I think I'm taking this Minkowski sum. I'm replacing it with, instead of in this case, instead of a sphere, I'm replacing it with a square. So it would be something like that I get, because I'm taking slightly bigger body for my Minkowski sum. So let me just complete that formula. So I divide by delta. And this is now very easy to compute, right? Because it's a convex body. So if you scale it, the volume just goes up as you would expect. Right? The volume goes up 1 plus delta over R to the power n. That's what happens with scale convex bodies. So this just gives me exactly n over R times volume of K. Right? Because the volume of the scaled body K is 1 plus delta over R to the power n. Okay? And I'm removing K, I have to subtract the volume of K from this. So I'm just getting, as delta goes to 0, I'm getting n delta over R divided by delta, so I have n over R. Is that clear? Yeah. Okay. So again, this is a basic bound on the surface area. I don't know if it has a name. It's something we use extensively. So this is just telling us that containing a big ball is good, right? Even though if you think in terms of volume, the ball is tiny compared to the convex body. Typically in high dimension, this ball in n dimensions will be exponentially small compared to the body that it's containing. That's typically what you get in high dimensions. And nevertheless, it can give you this very interesting information about surface area. Okay. So why am I telling you this? Because that allows us to give a very easily construction of good bubbles, good foams in n dimensions. The trick is to use very useful fact from lattices that says that if you take a random determinant one lattice lambda, and I won't define exactly what I mean by that, but there is a well-defined notion of a random lattice. So basically you start with z to the n with the integers and apply some random linear transformations. It will converge eventually to something like that. But there's a clear notion of the R measure, R and Ziegel measure on the space of determinant one lattices. And those have very nice behaviors, those random objects. One of the nicest things about them is that there is a theorem due to Ziegel that tells you that, take basically any set in space, the expected number of lattice points in a space is in the set is exactly the volume of the set. So Ziegel proved that I take any set that I wish, the number of points I find inside is kind of what I would expect based on its volume, because the lattice has determinant 1, so it has 1 point per unit volume. If you use this fact, you immediately get the following property. So I'm just basically giving you a proof of the following property. So it is known, and again, it follows from this Ziegel theorem, it is known that with high probability, lambda one is the notation I use for the shortest vector in the lattice, the non-zero vector. 0 is always there, but the non-zero vector. this is at least here. This is at least square root of n over 2 pi e. And why is that? That's precisely the radius of a ball of volume 1 in n dimensions. So this is how Ziegler connected, because Ziegler tells you, take this ball, with good probability, you will not have any point inside it, because the expectation is less than 1, much less than 1. So let me just define where, what is this lambda 1? Lambda 1 of big lambda is the length of the shortest vector in the lattice. Okay. So why is this so nice, right? This is so nice because if you take this lattice, and now what you want to take the Voronoi cell of the lattice. You want to take the cell defined like this. Therefore, the Voronoi cell, which is simply all the points that are closer to the origin than to any other lattice points. Okay, so like the hexagon we saw in the hexagonal lattice, it doesn't the natural way to divide space based on the closest point in the lattice. So Voronoi is defined to be all points in Rn such that the distance from y to delta to lambda is just the norm of y. In other words, 0 is the closest point. You can't get closer than to 0. So Voronoi has naturally defined partition of space. They're volume 1 because those are fundamental cells. There is one of those Voronoi sets per lattice point. Again, just like you saw with the hexagons, if I go back there, one hexagon per lattice point, same thing. And what's nice about them, because we know that the lattice has no short vectors, we know this Voronoi cell must contain a ball, because as long as you're closer to the origin than, I guess, half the number here, you're guaranteed to be closest to the origin, because there's no other vector anywhere near. So this lattice has this amazing property, despite having determinant 1, like z to the n, there are no short vectors. So as long as you're not too far from the origin, you're guaranteed to be in the Voronoi cell. In other words, the ball is contained in the Voronoi cell. So if you take this Voronoi cell, it contains the ball of radius that's half of what I have there. So half times square root of n over 2 pi e. It's really by definition, because any points in this radius must be closest to the origin. And now we're happy because we have now big ball inside that tiling body. And by claim 1, has surface area, which is at most 2 times square root 2 pi e n. Yeah, so the lower bound, the gap from the lower bound is just a factor of 2, right? This is square root 2 pi e. This is 2 times square root 2 pi e, and their isoperimetry gives you square root of 2 pi e again. Yeah. Yeah, so this, I don't know. If you want to improve on, yeah, but yeah, I'm trying to think of like sphere packing, where you could ask like Minkowski's theorem versus just the volume, just the volume bound. Yeah, so I don't know. Yeah. So that's basically the proof. Okay, this is the proof. Well, it's not the new result, but yeah, this is what it's not the main result. This is the introduction. Yeah, this was yeah. So this was is this convex? Yeah, the Voronoi is always convex. Okay, but this is not the main result. It's still the introduction. Yeah. So okay, so if it's not known, great. We have another result. But it is known. It was mentioned in papers I mentioned in the next section. It was already mentioned in at least one text. Okay, so it is a spherical cube you can say it's really spherical because it contains a ball. It's also contained in a ball. I didn't talk about it, but it's even contained in a ball. So it has good surface area. It's not only contains a ball. It's amazing cell, but it's not. Sorry, it's a spherical tile, not a spherical cube. So what is spherical cube? That's next. That's the next topic. This is not spherical cube yet. This is just a way to partition space. It's a tile. It's a foam. What's missing is the integer structure. What's missing is z to the n. So the answer is I'll get there next. Exactly. So this is where things. Kelvin asks for any form. It doesn't have to be. It doesn't have to be lattice. Can be anything. Right. Right. Oh, you found that reference where? Okay.
Actually, yeah. He was talking about the partitioning of field of rings and specifically said of rings.
No, this is hexagonal. So this is hexagonal. No.
This is not a question.
It's too late to ask him what exactly he meant, but there are two variants, and this is one variant. And let me show you the other variant. But we asked that too. I mean, what is the minimal surface area? So what we care about of z to the n periodic tiles, or bubbles or tiles. Yeah. Okay, so that's really where our story begins. This was first, or maybe it's already asked by Kelvin, but this was already also looked at by Choi in 1989, and he found out the optimal answer in 2 dimensions. I can show you. I have it here. It looks something like, oops. So this is of course 4, but he found this. So what's special here, if you can see, is the centers form the integer lattice. This is z squared, just the integer points. But if you look at the surface area here, it's better than the square. Square would be the naive thing to do, of course. So squares, again, are an answer. It's 4. This gives you 3.864, those kind of hexagons. And this is also optimal. They form those angles of 120 degrees. Choi proved it's optimal, apparently, among all partitions. So, you can take this question also in high dimensions, which is what we care about. So in n equals 3 in 3 dimensions, of course, it's open. So, but there's a nice construction that achieves something non-trivial, and that's the one here. And let me show you. Okay. So this actually comes from a paper. You might be wondering, why am I talking about this in the CS seminar? So this comes from a paper of CS people. This was Kindler, O'Donnell, Rao, Wigderson in 2008. And previously it was asked by Feige, Kindler, and O'Donnell, and also by Ran Raz, who basically understood that this question actually has surprising connections to parallel repetition and to specific games known as odd cycle games. So basically, Ran proved some surprising results about repetition of those odd cycle games. And Kindler, O'Donnell, Rao, Wigderson made the connection to this question about, or showed also implies the result for foams. And here's what they proved. So this, by the way, this figure, including others I've shown, come from the KORW paper. So credit goes to them. And for large N, they showed, this was a surprising result, that it's most 4 pi square root N. You can actually generate, you can build, they exist, such tiles exist that give you surface area of 4 pi square root n. This is K, O, R, W. And later, Noga and Boaz Klarreich, actually both today here in Princeton. And they show that this, you can actually, those things exist. And again, if you think this basically, just like in the case of arbitrary forms, this basically settles the asymptotic question. Now we know that the answer is square root n. Their construction, however, for the n-dimensional body is somewhat surprising or counterintuitive. It's highly non-convex. It's highly non-convex. It's also probabilistic. And here's, let me show you roughly how it goes to get a sense of what it might look like. So they start with a fixed, well-defined body. It looks something like that in 2 dimensions. Okay, you can write down explicitly what it is. This is a nice body, except it doesn't really fill the space. It doesn't tile. At least they don't touch each other. So it packs, but it doesn't cover. So it doesn't tile the space. What they do next is say, okay, let's randomly shift this body. And that's what you just saw here. So this was the big path. Let me show it again. You start with this body, you randomly shift it. Everything is kind of done modulo the lattice, modulo the torus, modulo 1. So you kind of shift it, and then you add all the parts that are not already there in the previous body. So you're adding this new region that you covered. We do it again. And at this point, when we do it again, we covered all of space. And this gives us our body. That's what it looks like in 2 dimensions. It's a randomized construction. That's what it gives, this very strange body. And it turns out this has the surface area, at least on average of 4 pi square root n. So again, the idea is to take some body and randomly shift it. The construction is kind of maybe surprising that this would work. Once you think about it a bit, you realize that those random shifts are very natural thing to do. So this, again, up to constant, this question is settled. And I should say that this generally building those tiles is quite rigid, quite difficult. And there's recent work of Mark with Dor Mincer. And let me just mention it briefly before I really go to the new results. So Mark Beverman and Dor Mincer in 2020 show that if you impose some other constraints on this body, like they wanted some axis symmetry, then you can't do it anymore. Then suddenly the surface area goes up to almost n, so like the cube. So for axis symmetric, the details don't really matter. I just want to show you that once you try to impose additional constraints to make this body look a bit more tame, you cannot do it anymore. So for axis symmetric tiles, they actually show the tight answer of n over square root log n. So jumps up to n. So the question we care about finally are convex cubical foams. Okay. So what this means is that we want to use convex sets. We want to tile space using this convex body. This is very strong restriction. To tile space with a convex body means that you have to be a polytope. You must satisfy many properties. It has a name. It's called a parallelohedron. So you can't just do any crazy convex body. It really restricts the kind of bodies you can use. So currently nothing better was known. Nothing better than 2n was known, or slightly better was known, but nothing much better, I should say, than 2n was known. 2n was known. So you can improve a bit the constant, but it was still n. And what we prove, the theorem, is that you can actually get close to square root n. So there exists a parallelohedron. So I'm introducing more terminology. It just means a set that ties, a convex set that ties space. So a convex polytope. So there's some disagreement. Yeah, the Venkov, the Russian, I think, called it parallelohedron. Then someone changed the parallelotope. The notation is always confusing because it reminds me of polyhedron, but it's the key is the parallelo part. So convex part of the tiles Rn. Tiles Rn. Those are, again, very rigid bodies with Zn. Right? With Zn translates. So what we saw already, we saw this Voronoi cell. It was already a parallelohedron. It tiled space. It had good surface area, but it was not tiling with Zn. It tiled with some random lattice. This tiles with Zn, hence surface area. And surface area of almost square root n. So it's square root n times exponential in square root of log n. Some lower order terms, but it's up to those terms, it's square root n. So again, those bodies are quite rigid, those parallelohedra. It seems like there's not much you can do. In fact, there's a celebrated conjecture of Voronoi from 1909 saying that those are basically Voronoi cells. So you can't go much beyond Voronoi cells, up to affine transformations. This is still wide open. It's a very nice conjecture. What is known is results of Venkov and McMullen that characterize those bodies. They're quite, as I was saying, quite rigid. They need to have satisfy some properties. I'm just saying it because there's only that far you can go to search for those bodies. And I think this is why some of us thought that this probably would not be the right answer. Maybe some of us thought omega of n would be the right answer, but turns out that it's actually a construction that gets you square root n. Okay, so let me try to give you the proof idea. I will not show the whole thing, but I'll give you the main idea, and you see how to get a construction that gets close to, goes below n. I won't get to square root n. So the basic idea is this. I mean, we want to find a tile in Zn. The reason we have so much trouble is that Zn has all those pesky short vectors, like 1, 0, 0, 0, 1, 0, minus 1, 0, 0. Ideally, you want to get rid of them. This has been used in several results that I know in computation. I know that Subhash Kott has a paper on hardness of lattice problems where it sparsifies the lattice. So the thing is that Zn has those pesky vectors, but there aren't so many of them, so maybe you can get rid of them. It's not clear how to do it here, how to get really rid of those vectors. So what we'll do is this. We'll just find a subspace. We'll find a subspace where we don't have, right? Find a subspace containing no short vectors, no short integer vectors. And basically take a Voronoi cell inside it. And take Voronoi cell inside it. Voronoi cell inside it. So that doesn't make any sense. I mean, I can find a Voronoi cell inside a subspace, but I care about tiling of all space, not of the subspace. Subspace. Well, yes, that would not be good. Yes, so I need some extra properties. You're saying if I'm going some irrational angles again, but it's going to have lattice points inside it. Let me show you an explanation of how this works. Unfortunately, I can only do it in 2 dimensions. We have to think this is actually n-dimensional and try to imagine what it would look like there. So I start with z squared, the integer lattice, and I want to identify a good subspace. So how will I do this? Let me take a vector. In this case, I would take this vector here. This is the vector -1, 2. And let's take everything orthogonal to that vector. So I take an integer vector and take everything orthogonal to that vector. This gives me this subspace. Okay, again, it's 1-dimensional. I'm limited here, but imagine this would actually be very high dimension, almost n-dimensional. So we'll find a high-dimensional subspace doesn't contain any short vectors. The shortest vector here is square root 5, right? It's the vector 2, 1. And what you can do inside a subspace, you can take a Voronoi cell. Again, here it's all looks. This thing here, this is the Voronoi cell. Right? This is a Voronoi cell inside this 1-dimensional lattice. You can see it's kind of contains a big sphere. It's 1-dimensional, so there's not much you can see here, but it contains a big sphere because there are no short vectors. What do you do next? Well, you want to lift. You want to lift that Voronoi cell to the big space, and here is how you would do this. notice that whenever you have a subspace like this, you can actually look at all its cosets, and you can see this partition of the whole lattice into those cosets. So I have kind of the subspace, then one coset, two cosets, three cosets, so we have all the cosets of the subspace. And what I want to do is basically take each of those Voronoi sets in my subspace and lift them a bit. I multiply them by something else in the orthogonal direction. In this case, it will also be an interval because we are in one dimension, and that's what it looks like. Right? So I turn this into, in this case, a rectangle, and I just use that to tile space. So let me show you again. This is a rectangle, and by kind of moving it over all those cosets, I get a tiling of space. It's kind of brick wall-like tiling space. I should mention that it will help us later. How tall is this rectangle? That really depends on how long this vector here was. This vector here is of length square root 5, and you can see that this is square root 5. This vector square root 5, and this would be 1 over square root 5. And it's not a coincidence; those are reciprocals because there's some duality going on. So when you project orthogonally to vector some subspace, you get something like that. This is between the cosets is like reciprocal. So yeah, because I already told you that the volume here is square root 5. The volume has to be 1 because it's a fundamental body. Okay. So this is basically the idea. And to do that, we'll have to use another simple claim about convex bodies. So if I multiply two convex bodies like I did here, like some kind of Cartesian product of two convex bodies, then what is the surface area? So think if I take like a cylinder, I multiply like a sphere with the interval. So what's the surface area? Well, I have the sphere here, another one kind of hiding below, right? 2 times the surface area of the sphere. 2 because the 2 is the surface area of the segment. It's a 0-dimensional boundary. And I also have the surface area here, which is the perimeter of the circle times the area of that interval. So basic statement in geometry. So what I claim is this, that it's the volume of the surface area of K is the surface area of linear space times the volume of K2 plus the other way, volume of surface area of K, volume of K1 times the volume of surface area of K2. And if I divide everything by volume of K, I'll get a nicer form, the form I want you to remember, that the volume of the surface area of K divided by the volume of K is equal to the surface area of K1 divided by the volume of K1 plus the surface area of K2 divided by the volume of K2. And now you see why I like this quantity, surface area divided by volume, because it's additive under product. It behaves additively under product. It's very nice to work. The only non-trivial fact we need, is also not very difficult to prove, is that there is some nice construction of matrices, of 0-1 matrices, that have this K-wise independent property in the columns. So that's like the core non-trivial fact we use here. Again, it's not difficult. So I'm kind of hiding some technical details, but briefly it says something like that. So for any S less than N, there exists an M times N matrix, so 0-1 matrix, 0-1 matrix, with essentially S rows, so slightly more than S. So M is S log N, but forget about this log N, doesn't really matter much for us. Rows, such that, and this is really what we need, the first property is that any S columns are linearly independent. Any, at most, S columns are linearly independent. And number 2 is that number of ones in each row is 5n over m. Okay, the 5 is just arbitrary. It doesn't have to be 5, just something for concreteness. So these matrices, you might have seen them under other names of variants of this. You can think of it as some LDPC. You can think of it as some compressed sensing matrix. You can think of it as lossless expanders. Many names for this. This exact thing we haven't quite found, this exact variant, those parameters that we need, but it goes by many different names. The proof that those things exist, you can do it by the probabilistic method. Basically take a matrix and choose, say, 5 random ones in each column. This would work. I can provide more details later. Basically just randomly pick each column as a vector with 5 ones. Again, 5 doesn't matter. You can probably do it with 2. And I'm hiding some small details, but that's the idea.
Even over GF2. Yes.
That's how you prove it. Yeah. Even over GF2, we don't need that, but that's how you prove it exactly. Yeah. So we're looking for more references to see maybe there are explicit constructions, but that's I can mention it. Something like that should hopefully exist. We don't know. So let's just complete the proof. Now we have all the tools we need. We take a subspace. The subspace will be the orthogonal complement to the row span of the matrix, this matrix. So again, this matrix is going to be very kind of fat, right, and short. This will define a very high dimensional subspace that does not contain any short vectors because of the linear independence properties. It's like some kind of parity check matrix. So let A be as given in lemma 3 with, let's take S equals square root n, and M is similar, and M is also, number of rows is similar. M is roughly square root n. There's some log n there, but it's forgettable. Okay, so again, square root n by n matrix. Let V be the row span, of A. So this is a low dimensional subspace, square root n dimension. And that's the vector I chose, if you remember in the picture, it's vector of n square root 5. And now any point, this is really the key, the first key idea, right? Any point that's orthogonal to V, right? Any integer point orthogonal to it, kind of by definition, it must form linear combination of the columns of this matrix because it's orthogonal to its row span. But that means it must have lots of ones because there is no linear dependency among S columns. So if there's any linear dependence, it must be of Hamming weight at least S, which means it's a long vector. So any point in the space has more than S non-zero entries. And therefore, the shortest vector is bigger than square root of S, right? Because the L2 norm is at least square root of S. There are, because the next fact, right, because integer, everything, you can solve, yeah, there are. But because I know that the orthogonal complements, now I'm going to project on V, the whole lattice. So if there won't be any points there, it should become dense.
You care about points of the left.
Yeah. I mean, just to solve the equation, you'll find some integer combination of the columns that adds up to 0. Yeah. But if there aren't any, I'm only happier. But the statement is still correct, but I'm not using it explicitly. So why do we care about it? Because we know if we take the Voronoi-Cell inside the subspace, it's going to have a very low surface area because no short vectors, right? So by claim 1, if you remember claim 1, if I take the Voronoi-Cell, if K1 is the Voronoi-Cell of this intersection, the volume of the surface area of K1 divided by the volume of K1 is at most n. It's actually n minus a little bit, n minus square root n, because we're in slightly smaller dimension, but n over square root s times, which is n to the 3 quarters. So this is relatively low surface areas, less than n. But we're not done, right? This is just inside the subspace. We have to lift. How do we lift? So moreover, since the rows, so remember the square root 5 and the 1 over square root 5, we have the same thing here. The rows of A, and I'm hiding a detail, are almost orthogonal. Yeah, I haven't proven that, but because they're almost orthogonal, and they're of length square root of 5 n over m, and of length square root of 5 n over m. You know that if you now have look at this direction of v, you get a lattice that's not too dense. So you get the projection on direction v of zn. That roughly looks like basically the integer lattice scaled by m square root of m over 5n. Okay. So basically, we're getting a very simple picture if you just project everything on the subspace V. So orthogonally, there are no short vectors, everything is good. But in the subspace V, if I look at the cosets are relatively nice configuration. It looks basically like the V to the M. M is, again, remember, M is small, M is like square root n. And now we can just lift like we did before. Before we had to lift with an interval, now we can lift with a cube. So we define if K2 is a cube, a scaled cube, because I want to, again, lift to that subspace in V. The volume or the surface area of K2 divided by the volume of K2. So it's basically a cube, but it's scaled down. So I'm losing that factor where I scaled down by. I told you it's -1 homogeneous. So scaling down actually makes me lose a bit in the surface area. So 2m is because it's a cube, and I have to add this extra factor because I'm scaling down. That gives you 2 square root 5 n to the 3/4. So together, you're basically done. So together, K equals K1 times K2. So after we lift it, this is a tiling body, as we want, is a tiling body of Zn, a tiling body of Zn with volume of the surface area being n to the 3/4. I'm just adding the 2 up. This is using claim 2, plus 2 square root 5 n to the 3/4, and that's theta of n to the 3/4. So it's not quite square root n. I promise you square root n. This is n to the 3/4. Question: how do you improve it? So this is the first scale iteration. You can actually improve it. I did one thing here what wasn't very optimal. It was right. What I'm doing here, I'm just using cube, but at this point we already know cube is not the best way to tile space. Yes, so you do it recursively. All you have to do is now take this cube I use here. This is why I have a 2m, and I replace it with a better tiling of z to the m. And the next step will get you from n to the 3/4 to n to the 2/3. And you can have to keep doing it and make sure it's actually somewhat of an annoying recursion, because even though you can go to much lower dimension, you actually lose a lot because everything becomes so much denser there. So generally there's just more surface area. So it's kind of too many things pulling on the strings there. But if you do the math, you end up with something very close to square root n plus some low order terms. So I'll finish this. Okay, so eventually S will be something like that. S will be n over something exponential in square root log n. Yeah, so it has more than any polynomial, yeah. Yes, the number of steps has to be very carefully controlled because you lose a lot in each iteration. So this forces you to do square root log n iterations. each time you gain this e to the squared log n. So just briefly, some open questions. I mean, this what we had. What I showed you today is that there's a body that tiles space with the shift of z to the n. Where this could be potentially de-randomized. We just need to know how to construct this matrix. If you want, you can have explicit construction, which was not possible with previous construction, as far as we knew. Another open question is, of course, to improve and get square root n, get exactly square root n. I don't know, maybe it's impossible. Maybe you can show lower bound. We are currently stuck. And that's it. So let's stop there and take questions. Thank you. Okay.
Just the embodied lower bound. Suppose you again just want to improve the constant in the square root chain using, because now you know also the selective. You want to be better than the parametric quantity. So just to improve the lower bound. Some other constant types. So
it's no. There are other parametric replacements for surface area where this question isn't studied, like mean width. So you want to say a convex set of tiles are in and has small possible mean width. The direction you want to try to request know the direction of the average. So that is we solve exactly for example. Which I don't know, maybe that's relevant also to computer science. Maybe and the argument, and I think using that, and then what is it called the diameter? But mean width is a mixed volume. It's like a surface area. And then there is this unexample potential. I think you will get something better. The best value is not a cube. So that will give you something better.
Not a boom. Not a boom. No.
Whatever the best value will give you something better. Yes. Well, but I'm guessing you can get it from the.
But even so I think it might be easier for ZN to prove lower bound specifically for ZN. You can use it maybe.
Other quantities you could replace with a proxy for this area.
But that you could also do for other for any parallelohedron, anything that tiles space, not just for ZN. Okay.
I'm thinking of this as starting with a one-dimensional thing and then lifting it to one dimension up to the time in like a random direction. Something like this.
Yeah, I think those bodies, because of the thought, when I said rigid, it's not clear how to construct them. You can think that I mean, another thing here is happening here in that using the tiling is not face to face. If it's like a brick wall tiling, right? If you look at typically you think of tiling, you might think of like face to face things. Like this is brick wall, right? The faces don't really match; they're shifted. But if you think of hexagonal tiling, right, it's face to face. The faces, all those tiling and the faces are perfect match to each other. So you could ask another question is whether you can do it with face-to-face tiling. I would guess you cannot. Those are probably very restricted. But generally, the reason I'm saying it is because you could imagine maybe some. Yeah, I mean, you can try. Yeah, I mean, you can try that. Yeah. Which one? Okay. Right, like designs or combinatorial. Okay. Yeah, I think there's
so that the also the parameters are in the wrong. Because with these funny parameters, they never treat those parameters. But maybe
Yeah, I think that there is. Right, this is, yeah.
Your paper, you don't use it, you don't use this parameter.
Yeah. For instance, if you look at the explicit, the running time, for instance, if the ratio, the aspect ratio of the matrix is not constant, then the running time is not. So kind of they need the fact that there's a constant aspect ratio for the explicit part of it. But you can use it if you don't care about explicitness. Yes, you can use the unique, right? You can use unique neighbor expanders. And you lose a bit because they're not as good as these ones. Yeah. Yeah. I mean, they ask for something stronger, right? That any set of columns has sort of more neighbors than the. We don't really need that. We just need linear independence. Okay, thank you.